Section 1.3 is on page 26, talks about propositional equivalence. We start off with a definition of a compound proposition that is always true, no matter what the truth values of the propositional variables that occur in it is called tautology. A compound proposition that is always false is called contradiction. And a compound proposition that is neither a tautology nor a contradiction is called contingency. That's like the traditional. An example, if I take P, if I take the negation of P, now if I take P or not P, so, or one or the other or both, since one of them is true, both of these are true, this is a tautology. If I look at P and not P, so both statements must be true, you look at those two, since one of them is false and the other is false, there it is. This is a contradiction. So that's always how it works. Make that a bit nicer. Got it. Now, definition 2 talks about equivalence. The compound proposition P and Q are called logically equivalent. P if and only if. So remember, if and only if works forward and backward. If then if. So it works in both directions. The only way that would work if the original is true, so if P is true, Q must be true, and vice versa. And if P is false, Q must be false, and vice versa. That's when there's no illogical argument there. The illogical argument when one of them is true and the other one is false. That's an issue. So we say P and Q are logically equivalent if P implies Q is a tautology. The notation, an equal with an extra line, indicates equivalence. Do you know that P and Q are logically equivalent? There's a remark you should pay attention to. The symbol, an equal with another line, is not a logical connective. And P is equivalent to Q is not a compound proposition, but rather it is a statement that P if and only if Q is a tautology. Something you need to remember as we run by later on. And the symbol is sometimes used instead of equivalent to denote logical equivalence. Well, to us, we just have to realize what are those. So example 2 on page 38 says, show that, so let's look at P. P, true or false. Negation of P would be false, true. And the negation of this, so if I take the negation of that, that will be true, false. So it says, show that the negation of the negation and P are logically equivalent. Do you see that they have the same truth values? And there it is. So we say the negation, again, I'm going to use this just for simplicity reasons. And there it is. Use truth table to verify the associative law. This says if you take P or Q first or R, that's equivalent to you taking P first, P or R, and then take P or that. And works the same way. Let's make sure we get that. So there's P. We have 3 of them, so we need 8, as you know. 4 of those. 4 of those. 2 each. And alternate. Now, I'm going to start with the first P or Q. P or, whenever one of them is true, they're automatically true. So I'm looking at those two. That's true, 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 false, false. So all of these are true except for the last two. So if it's or, the only way they would be false if they both are false. Now, if I take P or Q or R, now I'm looking at those two. And you notice if one of them is true, it's automatically true. So the only false is the last one. So all of these are true, except the last one is a false because they're both false. Now I'm going to go for Q. Let me see what I'm missing. Oh, I'm going to go for Q or R. Q or R. Those two, Q or R. Again, if one of them is positive, if one of them is true, it's automatically true. True, true, true. That is false. True, 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 and that is false. So all of these are true except those two. Now, we want to check P or Q or R. P is right there. Or, so I'm looking at those two. If one of them is positive, it's automatically positive. So that's, if one of them is true, it's automatically true. Since this is true, 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 I gotta check this. This with that, since that is true, it's true. True, true, true. And since this is false and that's false, that's the same thing. Whoops. And now I'm matching. Let's see what they're asking. They're asking for us to look at this and this. They're saying, are those equivalent? Well, let's see. They're all true except the last one. So yes, it is. Use truth table to verify. We verified. And I'm going to leave B. Let me see. And yeah, that would be some work actually. Yeah. So I'm just going to do part A. I'm looking at number 6. This is De Morgan's law. This is something that we're going to use on the long one. It says use truth tables to verify. Okay, I have P and Q. So true, true, false, false, and alternate. Now if I take P and Q, remember the only way this is true if they're both true, which means all of these are false except for the first one. Now if I take the negation of that, wouldn't that become false and everything else is true? So there's that case. Now we want this case. If I take the negation of P, well, there's P. Isn't that false, false, true, true? And if I take the negation of Q, there's Q. The negation of Q would be false, true, false, true. And if I take this or this, well, if it's or, the only time it's false when they're both false, otherwise it is always true. And if I look at those two, I notice they are the same. So yes, that does work. And this is De Morgan's law. It says if you're taking the conjugate of and, that's the conjugate of P or the conjugate of Q, something you need to remember. And similarly, if I'm taking the conjugate of or, that's the conjugate of P and the conjugate of Q. So you could take the negation of each of those statements and switch the or to and the and to or. If I look at number 8, use De Morgan's law to find the negation of each of the following statements. Kawame will take a job in industry or go to graduate school. If I want to use De Morgan's law to write the negation of this, I would say K will not take that job and will not go to graduate school. Yoshiko knows Java and calculus. The negation of that, Yoshiko does not know Java or does not know calculus. C. James is young and strong. The negation of the and, James is not young or he is not strong. D. Rita will move to Oregon or Washington. The negation of that, Rita will not move to Oregon and will not move to Washington. So remember, if it's Oregon or Washington and you want the negation of that, then that's going to be the equivalent to the negation of O and the negation of W. Just saying. Problem number 12. Show that each of the conditional statements is a tautology by using truth tables. All right, so we have a lot of those. Well, we have P, Q, we have R. Now, I start with P implies Q. If then, remember, P implies Q. The if part is true, so I'm looking at those two. The then part must be true. The if part is true. The then part is false is the only problem with this. Because if the if part is satisfied, the then part should be. If the antecedent is false, the outcome is automatically true no matter what. So if it rains, there must be clouds. If it doesn't rain, there could be clouds, there could be not clouds. Either way, it's acceptable. Now I want to check Q implies R. Those two, the same deal. True, true. The only time you have an issue when you have a true and a false, like right there. If this is false, it's automatically true. Those are true. This is the issue again. And if the antecedent is false, this is automatically true. Now I want to take P implies Q and Q implies R. So now I'm looking at those two. Remember, it's and. The only way this is true if they're both true. So this is true. This is true. This is true. This is true. And the rest, since there is one false in there, those are automatically false. Hopefully I didn't make a mistake. Okay, now if I go for P implies Q, P implies, I'm sorry, R, P implies R, I'm looking at P and R. Remember, the only issue there, if this is true and that's false. So true and true is fine. This is an issue. This is an issue. If this is false, all of these are true automatically. And there it is. And now if I'm going to do the whole thing, so let me do it this way. Let me call this A. Let me call this B. And if I take A implies B, So now all what I'm doing, I'm matching if then. Well, the only issue when this is true and that's false, that's fine, that's fine, that's fine, and that's fine. So all of these are true. If the outcome is all true, then that is automatically a tautology. And that's really how it works. Now on number 18, I want to really point a couple of things out. On number 18, you could use arguments. You could argue yourself that this is a tautology, meaning that's going to be the same thing, or you could show it. The author really tries to reason this. If it's simple for you to reason, that will be good. We are going to focus on that later on. For now, using a table is okay. So think about it. If this is P and this is Q, and I'll elaborate what that means in a minute. Q is true, false, true, false. So let's see. They're saying determine if it's a tautology. Well, if I go for the negation of P, if I go for P implies Q, so the only issue is right there. If this is true, then that's false. If these are false, this is automatically true. Both of these are true, there it is. And now, if I go for, oh, I need to space that a bit better. Now, if I go for negation of P and P implies Q, so basically this direction. So the only issue would be when this is true and that's false, that's not the case. If this is false, these are automatically true. And then I go for the whole thing. Now call this A, because that's a big mess. And let's see if A implies the negation of Q. Well, I need to put them backwards. So no need to rewrite. You could rewrite it if you wish. Actually, here, let's do that. Let me list the negation of Q right there. Negation of Q, remember there's Q. That is false, true, false, true. And let's see. I called it A. If A implies negation of Q is always true. Is it a tautology? Well, let's see. Go in this direction. True, false. Automatically, just by getting this to be false, it's not going to work. This is true. There's another false as well. It's not only one false, it's a couple of false. So no, it's not. And if I look at this, again, try to use, this is a bit simpler. Try to use logical thinking. Remember how this works. P if and only if Q, the only time they are logically sound if they're both matching. Remember, this is one or the other. This is like me saying, hey, you want to buy a car, we will give you either $3,000 off or 2% interest. So this or is not the same as the English or, one or the other or both. This is literally one or the other. I'm sorry, it's not like the mathematical or. Or in math means one or the other or both. This or is literally like the English language. When you say, hey, you could buy a computer, we will either give you a free mouse or a free keyboard. You could get one or the other, not both. So for those to work, remember, one of them has to be false, the other one has to be true, right? But the negation of that would indicate that they're both true or they are both false. So those two would be logically equivalent. That's the same thing. And if you're not certain, for now, go about it the long way, but try to justify it the way I did. So if I take, remember, this means one of them has to be false for it to be true. If they're both true, that doesn't work. That's not allowed. And if you didn't take any, that's also an issue. What's the negation of that? The negation of this is true, false, false, true. And if you really think about it, that's really P if and only if Q. P if and only if Q is find right there and find right there, because those are the same, right? But if one of them varies, it doesn't match. And there it is. So pretty much, this is requiring one of them to be true, one of them to be false. This one requires both to be true or both to be false. But when you take the negation of one of them being true, one of them being false, that's automatically both true or both false. I didn't really need the table. I could have used that logical thinking. And that's pretty much it for this section.